Very good morning to all of you. Today I want to start session 8 of module 3. Title of module 3 is lateral earth pressure. This is the part 2 of module 3. Course outcome is given for the module 3 of second part, that is ability to compute lateral pressure distribution behind earth retaining structures. Title of subject is Applied Geotechnical Engineering and the subject code is 18CV62. It comes in 6th semester of civil engineering. So last sessions we have discussed about active earth pressures. Now I want to discuss about passive earth pressures. Passive earth pressures. Passive earth pressure occurs when a retaining wall is forced to move towards the retained soils, is nothing but a backfills. Passive earth pressure occurs when a retaining wall is forced to move towards the retained soil, is defined as a passive earth pressures. Means in simple sentence, retaining wall is moving towards the backfill is defined as a passive earth pressures. Passive earth pressure condition will develop if the wall moves a sufficient distance towards the backfill. The lateral inward movement required to mobilize the full passive pressure condition is approximately 0.01 times H for loose sand and 0.05 times H for soft clay, where H is the height of the wall. The passive earth pressure distribution can be calculated using Rankine's theory or Coulomb theory. The passive earth pressure is determined based on Rankine's theory or Coulomb theory. Now let us see about Rankine theory to determine passive earth pressure. Rankine theory assumes that there is no adhesion or friction between the wall and the backfill soil. The retaining wall is vertical and the backfill soil has a horizontal surface. So these are the assumptions of Rankine's theory to calculate passive earth pressures. I will read out once again. Rankine theory assumes that there is no adhesion or friction between the wall and the backfill soil. And second assumption is the retaining wall is vertical, and the third assumption is the backfill soil has a horizontal surface. So these are the assumptions of the Rankine's theory to determine passive earth pressure. The Rankine's passive earth pressure theory assumes that every soil element within the sliding wedge is on the verge of failures, as shown in figure 7.14a. I will show later, as depicted by Morse circle shown in figure 7.14b. Means see, this is the Rankine's passive local earth pressure. So this is the retaining wall. Wall should be vertical and backfill is horizontal, and this is the backfills, and this is friction wall, that is del, and these failure planes. So these are the failure planes acting at an angle theta equal to 45 minus pi by 2. Okay, means this is wall is moving towards the backfill, we are defining as a passive earth pressure, and these angles, that is failure plane, is x at an angle theta equal to 45 minus pi by 2, and this side is minus theta. Okay, this side is plus theta, this side is minus theta, means right side minus theta, left side plus theta. This is the rotation points. So this point is rotation point, means vertical wall is moving towards backfill is defined as a passive earth pressure, and this distance is del, that is frictions. And see this figure 3. So based on the horizontal lateral stress and vertical stress, we are plotting the Morse circles and we are locating Morse failure criteria. So along x-axis we are selecting normal stress, along y-axis we are selecting shear stress. With respect to normal stress and shear stress, we are plotting the Morse circles. And so this Morse circle is for the condition of at rest conditions, that is lateral earth pressure at rest conditions, and these are the passive conditions. So these are the passive conditions this failure envelope is developed. Okay, and this is Morse failure envelope, that is it is denoted tau equal to C plus sigma tan phi concept, and this is the angle of internal friction phi value. Okay, so this two figure is defined as a figure 7.15a and b shows the passive earth pressure distribution exerted on the retaining wall. The pressure is divided into two parts, that is Kp into gamma into Z and 2C times root Kp. So these are the equations to determine the passive earth pressures. Okay, so let us see from the figure. This Morse circle represents the stress condition in a soil element located at a depth Z below the top surface of the backfill. For reference, Morse circle for the at rest condition is also shown in the figure. The at rest stress condition occurs when the soil is stationary. When the wall starts moving towards the backfill, the lateral stress sigma dash h increases while the vertical stress sigma dash remains essentially constant. The limiting condition occurs when the Morse Coulomb failure criteria becomes tangent to Morse circles. At this condition, the lateral stress reaches its maximum possible value, termed the passive lateral stress sigma dash p. Morse circle predicts two sets of failure planes with theta equal to plus or minus 45 minus 5 by 2, as indicated in figure 7.14a and b. From the limiting failure condition represented by the Morse circle shown in figure 7.14b, we can show that sigma dash p, that is passive earth pressure stress, is given by this equation, that is sigma dash p is equal to sigma dash v times tan square of 45 plus 5 by 2 plus 2c tan of 45 plus 5 by 2, or it is also given in terms of sigma dash p equal to Kp into sigma dash v plus 2c dash times root Kp, where Kp is the passive earth pressure coefficient given by Kp equal to tan square of 45 plus 5 by 2. So this is the equation to determine coefficient of passive earth pressure Kp. For the case of a moist backfill soil with a deep water tables, the effective vertical stress can be calculated as sigma dash v equal to gamma into Z, where gamma is the moist unit weight of the backfill soil. Substituting this equation into equation 7.21 yields sigma dash p equal to Kp into gamma Z plus 2c into root of Kp. This is equation 7.23. Figure 7.15b means these are the figure 7.15. Okay, so passive lateral earth pressure for a cohesive backfill without surcharge. Okay, this is the vertical wall of height h and water table at the base. These are the backfill properties, that is gamma, phi, c, and we are plotting the lateral earth pressure on the same concept of active earth pressure. Okay, this is the lateral earth pressure, that is pressure distribution diagram based on backfills. So we are calculating sigma p equal to Kp into h into gamma plus 2c times root Kp. So this is due to passive force, passive earth pressure with respect to cohesive soil, is equal to sigma dash p equal to Kp means this plus this, it's become actual passive earth pressures. Okay, so this is the calculation of passive earth pressure with different depth. Okay, from this you calculate. Figure 7.15b shows the passive earth pressure distribution exerted on the retaining wall. The pressure is divided into two parts, that is Kp into gamma z and 2c times root Kp, consistent with the case 7.23. The total earth pressure is the sum of the two. From figure 7.16a shows a retaining wall supporting a fill with a water table located at a distance h1 below the top surface of the fill. Means see this figure. So same this figure explanation in terms of active earth pressure. Now we are defining with respect to passive earth pressure. Okay, this is vertical wall, this is h1 height, this is h2 height. Water table is located at a depth of h1 and above the water table backfill property is gamma, phi dash, c dash, and this is the surcharge load, and below the water table saturated unit weights and phi in c. These are the backfill properties is given. So then how to plot the pressure distribution diagrams based on these conditions of vertical walls. So same, so this distance due to surcharge, that is Kp into Q, but earlier we have calculated K into Q. So this is due to surcharge, and this lateral earth pressure is calculated Kp into H1 into gamma. So this total distance is at a depth of H1, and for at a depth of H2 we are calculating this distance, that this plus this times 2c root Kp plus this pressure distribution diagram, that is Kp times H2 into density, that is gamma saturated minus gamma W. So here earlier we have used same concept, instead of Ka you substitute Kp. Okay, and here you add 2c times root Kp, but earlier we have deducted minor deductates in active earth pressure. That is the main basic difference. Okay, and this diagram is based on water pressure, that is depth into dense unit weight of water. Depth is H2 and unit weight of water is gamma W. So now this plus this we are getting total force exerted at the base, that is at the hill of the retaining walls. So this is the clear explanations about passive earth pressures, how to determine. So this title of figure is Rankin's passive lateral earth pressure for a cohesive soil backfills with surcharge. So here why we are adding 2c root Kp means force is exerted towards the backfill, so that's why we are adding, and retaining wall is moving away from the backfill means we are deducting. That is the basic difference between active earth pressure and passive earth pressure. That is, you should be remember the logic. From figure 7.16a shows a retaining wall supporting a fill with a water table located at a distance h1 below the top surface of the fill. A uniform pressure Q is applied at the top surface of the backfill. The wall is forced towards the soil, thus mobilizing passive earth pressure. Let us assume that the soil below the water table is fully saturated. The distribution of the effective lateral earth pressure and the pore water pressure are shown in figure 7.16b. At z equal to 0, we are calculating passive earth pressure sigma p dash equal to Kp into Q plus 2c times root Kp, and water pressure equal to 0. Figure 7.15b shows the passive earth pressure distribution exerted on the retaining wall. The pressure is divided into two parts. One is Kp times gamma z and 2c times root Kp. The total pressure is the sum of the two. Figure 7.16a shows a retaining wall supporting a fill with a water table located at a distance h1 below the backfill. The soil or the wall is forced towards the soil, thus mobilizing passive earth pressure. Okay, this is repeated, no problems. Okay, this sentence is repeated. So now you calculate at a depth Z passive earth pressure. So sigma dash P is given Kp into Q plus 2C times root Kp and U is 0. Okay. So now at a depth Z equal to H1. So passive earth pressure sigma P equal to Kp into Q, this plus this, that is Kp into Q plus Kp times gamma into H1 plus this, so that is 2C into root Kp. And water pressure at a depth H1 is 0 because there is no water, because water table is below the H1s. At depth Z equal to H1 plus H2, means at a total height H at the hill is given by the lateral earth pressure, that is sigma dash P is given by this pressure plus this pressure plus this pressure plus this pressure. Okay, see here Kp into Q, so this Kp into Q plus Kp into gamma H1s, that is Kp into Q plus Kp into gamma H1 plus Kp times gamma saturated. Okay, here based on H1 means this plus this Kpq plus Kp times gamma H1 plus H2 means Kp times H2 into gamma saturated minus gamma W, this gamma saturated minus gamma W plus 2C times root Kp plus 2C times root Kp. So then water pressure U equal to gamma W into H2. So this is gamma W in H2. So like we are calculating passive earth pressure at a different depth. To calculate the lateral force, we can simplify the pressure distribution using triangular and rectangular shapes as done in example 7.1. So that's same procedure is here. The area of each shape can be calculated separately to give us the lateral force that must be applied at the centroid of the respective shape. The sum of these lateral forces is the total lateral force exerted on the wall. The point of application of the total lateral force can be calculated by taking the sum of the moments of all the forces about the hill of the retaining wall and equating that to the movement of the total lateral force about the hills. So we are getting the y distance. So this is the concept of to calculate passive earth pressure distribution of the given retaining wall with the different height, with surcharge load and different water tables. Now Coulomb theory. How Coulomb theory is expressed for passive lateral earth pressure. See, this is the horizontal lines, this is the top of the retaining wall, and this is the retaining walls acting at an angle beta. Okay, and this top surface of the backfill is sloped, it is at an angle alpha, and this is wedge backfill, and this W is acting downward, means self weight of the backfill is acting downward, and resisting force R is acting at an angle phi, and this R is perpendicular to the backfills. And with respect to theta 1, theta 2, theta 3, we are locating pressure exerted for the backfill. And so this diagram is same equivalent to similar to active earth pressures Coulomb theory. So x axis we are selecting theta and y axis we are selecting passive earth pressure P, and now this curve is become reverse, that is convex, earlier is concave and convex shape of curve we are getting for active earth pressure and lateral earth pressure. So where there is a lower tangent peak point, so that points we are selecting as a critical angle, and this point we are selecting as a dp by d theta is equal to 0. So then theta equal to theta critical and P is equal to PP. So these are the explanations of the symbols for Coulomb theory. Okay. The Coulomb passive earth pressure theory assumes that a soil wedge with a failure plane making a critical angle theta CR with the horizontal is in the condition of incipient failure as shown in figure 7.17. The critical wedge is about to slide up the failure plane, thus generating a passive earth pressure against the retaining wall. The wedge can be treated as a particle that is subjected to three coplanar forces W, P and R, where W is the self weight of the wedge, which can be determined easily by multiplying the area of the wedge with the unit weight of the backfill. P is the resultant of the wall reaction against the soil, and R is the soil reaction against the sliding wedge. The force P makes an angle del with the normal to the back face of the wall. The angle delta is the wall soil interface friction angle, which can be determined from laboratory tests or can be assumed as a fraction of phi dash, that is angle of friction of soil. Usually you can assume that del equal to 2/3 of phi dash. The force R makes an angle phi with the normal to the failure plane. The internal friction angle alpha and the battered back face of the retaining wall with an angle beta. As shown in figure 7.17, Coulomb theory considers a trail wedge with a failure plane making an angle theta with the horizontals. So from these figures, so these are the explanation with respect to these figures. Okay. The critical wedge is a next. If at failure, two equilibrium equations can be written, that is along the x and y axis, assuming an impending motion condition. Those two equations involves three unknowns, that is P, R and theta. Thus there is a need for a third equation involving sum of the three variables. Note that P, W and R are the functions of the angle theta. Coulomb theory searches for the angle theta equal to theta critical that yields the minimum earth pressure P equal to PP. Thus dP by d theta is equal to 0. This is we are considering as equation 24. The solution of equation 7.24 will yield the angle theta criticals, and subsequently the corresponding minimum earth pressure PP can be calculated, that is passive earth pressure can be calculated. The Coulomb passive earth pressure coefficient for the general case, the Coulomb passive earth pressure coefficient for the general case shown in figure 7.17 is dependent on the angle of the back face of the wall, the soil wall friction and the angle of backfill slope. See, these are the parameters. This del angle, beta angle and slope angle alpha, beta, del. So these three symbols are dependent. Therefore coefficient of passive pressure is calculated by these equations, that is Kp equal to sine square of beta minus phi divided by sine square of beta into sine of beta plus del into 1 minus root of sine of phi plus del into sine of phi plus alpha divided by sine of beta plus del into sine of alpha plus beta whole square. This is the equation you should be remember to calculate Kp with the wall, the soil wall friction and the angle of backfill slope, this equation. So this is the most important equation you should be remember to calculate coefficient of passive earth pressures. Okay, these are the references are referred for to cover the module 3 of part 2 in details. Okay, so different textbooks with different authors and different IS codes are collected to cover this module 3. Thank you one and all. Okay, so now I have completed all the 5 module as per the syllabus. I hope all of you study well and will score as much as possible highest marks. Okay, good luck, all the best in your futures. Thank you one and all.